I'm very excited about our next guests. I first met them at the Census Tech Summit in Glasgow last November, and we got talking about space IoT, and long story short, here we are. Like many computer systems on Earth, satellite networks are typically managed centrally. Taking lessons from the IoT and treating satellite networks as an extension of IoT sensor networks, decentralized alternatives to time synchronization and coordinated tasking of satellite networks will today be presented. We now cross over to Glasgow, where we join Beth Probert and Agathe Bouis, who are PhD students at Strathclyde University. Beth, Agathe, the floor is yours.
Perfect. Amazing. Thank you so much, Chris. Share our screens and hopefully that will be working. Perfect. And we'll have. Wonderful. Okay, fantastic. So thank you, Chris, for that introduction. As you said, we are PhD students at the Applied Space Technology Laboratory at the University of Strathclyde. And to get started, we wanted to talk a little bit more about space systems in general. But even before that, potentially something more familiar to the audience here today is computer systems, which actually share a lot of similarities with satellite and space systems. So particularly in the world of IoT, you might be familiar with a centralized architecture where you have many devices or many computers that all rely on some central authority, which could be a server or a cloud-based server or anything like that. And we can translate that into a satellite network where instead of a server, we might have a ground station or a central network of GPS satellites. They then connect outwards to other satellites, traditionally in low Earth orbit around us. So low Earth orbit stretches from about 200 to 2,000 kilometers above the surface of the Earth. And this centralized architecture is still used today. And this comes with some potential risks associated with it, where in this diagram, if you imagine that ground station or that central server is the red dot at the bottom of each of these diagrams, they become a single point of failure and a potentially large source of vulnerability in that IoT network or even in that satellite network, where if you were to attack it, and cyber attacks on satellite networks are becoming more and more common nowadays, if something were to happen to that ground station, you're not just losing the ground station, you're losing access to tens, hundreds, thousands of satellites and the services that we rely on. On the previous slide, we saw position, navigation, and timing satellites, which give us things like location services. So you can imagine the consequences of what would happen if something like our location services went down.
Yes, so talking about that, with central systems come central issues, which induce vulnerabilities, considering the ever-evolving cyber ecosystem that space systems represent, where in the last years, thanks to in part increased launching capabilities, we've seen increased numbers of satellites, increased access to space, not only from governments who used to be the sole people in space, but now also from private actors. We're seeing an increased reliance on satellite data, whether this is GPS data, GPS services with Earth observation, among other many suites of products, but also an increased number of bad actors, which tends to be a bit of a problem when we're seeing software becoming an increasing part of satellites, where satellites used to be very hardware focused. Now everything is software along with the links and data that we send, which means that we end up in a problematic situation where we're seeing an increased scope and impact of cyber attacks to space systems, whether those be exposure, interception, intrusion, interference, among another plethora of other problems. So what we are considering here, and is very much taking inspiration from IoT, is considering satellite networks very much as a system of different little entities, where we can imagine satellites, if we remove the Earth from sort of where they are, as a decentralized system where satellites are able to communicate with each other using inter-satellite link technologies, where their payloads allow each of the satellites to communicate with each other. So this means that we have satellite systems as a complex network where you can imagine, for example, that they're trying to get an agreement on some data, and that the colors that you see in these diagrams mean that they all have different state values at the start. And we can imagine them talking to each other with ISL networks, and for example, exchanging their time data. Which becomes problematic since, as we mentioned in the previous slide, we're seeing the same bad actors who obviously would like to disrupt, access, interfere with what we're seeing here. So this is what we're dealing with as sort of the foundation of both of the models that Beth and I are working on, which is a network that is sparse, where satellites are obviously very far from each other, so few communications. The network is dynamic, the satellites move with respect to each other. We're seeing time delays. Satellites are far, so any communication takes time. It's asynchronous, because obviously satellites are far. I feel like I'm repeating this. And unfortunately for all of us, there are some relativity effects, which, as I like to describe it, is somebody else's PhD. But moving on from that, what I'll be talking on first is this idea of decentralized time. Beth mentioned PNT, so position, navigation, and timing. And as you might know, timing and time synchronization forms a lot of the foundation of how satellites and systems, even in IoT, are able to have any coordinated tasking action. You need to have the same time to be able to agree on what to do and confirm that things are happening together. So what we're trying to look at is moving away from GPS-provided time synchronization onto a decentralized time synchronization, which becomes a problem of consensus. All the satellites here must agree on a shared time without any central authority. The consensus must be able to cope with disruptions, whether these be faults or the bad actors we were mentioning before, but also deal with the characteristics of space networks, so that is the dynamics, the delays, the effects, etc., which, as some of you might already be familiar with, are a lot of the characteristics that IoT networks tend to deal with. So how do we deal with that? Well, it's a decentralized protocol. The simplest approach, if you imagine just different IoT nodes communicating with each other, the simplest approach to get consensus is for them to exchange their data and for each node to evolve towards the mean of the data they have received. But unfortunately, this isn't resilient, because any extremist node that we might have, or with an outlier value, will be able to influence the entire system and create failures that will cascade, a bit like how we had a central authority failing. So the solution is a protocol that can filter out the extreme values that each satellite receives, meaning the protocol needs to be resilient, but more importantly for us, does not need any knowledge of the network topology or the type of disruptions it might be dealing with. Because if so, this is just a centralized system. If you know what your network looks like, if you know the type of disruptors and the number of them, we're back at square one. There's no point in trying to have anything decentralized if you have that knowledge. Which means that a lot of the fixed filtering or sort of consensus protocols that currently exist can be a bit removed or have to be, like, we cannot consider them, because fixed filtering relies on knowledge of topology and disruptions. Which led me to a fun and what I would like to call perhaps a creative approach to trying to get consensus and time synchronization, which is looking at crowds of people, and more specifically, social dynamics. So social dynamics, to sort of explain a bit of a background, is a model that in sort of a field of study that considers the way that people interact, and specifically the way that people in a crowd might change their opinions after coming in contact with each other. So you can see this, if you interact with somebody that you know, you will change your opinion based on what you've just said to each other. So this model assumes, however, that to mutually influence each other, two people that come in contact must have sufficiently close opinions, because if you have ever interacted with people who have a very different opinion from yours, you'll notice you will never agree. You will never change your opinion. If anything, you're more likely to become more stubborn, which is what this idea of tolerance tells us, which is that usually people who are very extreme tend to have a low level of tolerance for other people's opinion, whereas people who are more moderate obviously have a higher tolerance and are more willing to engage in discussions and change their opinions. Which, by the way, is the reason why we've seen rises in extremists among politics and political groups. Bit of an unfortunate thing, but very interesting for our modeling purposes. Which is what brings us to the first model and sort of consensus protocol that I'd like to present here, called Odyssey, or a bit of a mouthful, but the opinion dynamics-inspired disruption-tolerant consensus protocol. What it does is take inspiration from social dynamics. And so for this, bear with me a little, we imagine that a satellite, or an IoT node, if you will have received values from its neighbors or for the other IoT nodes that are connected to it. And from this, it can create a distribution of values from the data set that it has received. It can then establish what is the median of this distribution and where it stands with respect to this distribution values it has received. That is, a satellite will look at what its neighbors have said is the correct time, and it will think, am I far away from the center of this distribution or close to the edges? And what it will simply do is look at where it stands in this distribution and filter out all of the values that are more outlier than itself, meaning it will only consider the filtered values for its update and to change its current consensus status. So that's a bit of the premise that we have here, where if we go back to social dynamics, this is an inversion of what social dynamics typically do, meaning that a satellite that is very close to the center of the distribution, that is very close to the consensus, will be very, very stubborn, whereas a satellite that recognizes that it is an outlier will instead be much more tolerant to other people's opinion and will rapidly change that state towards what the others agree on. So to then wrap up this basis, what the synchronization process looks like, apart from the consensus itself, is this. A satellite network at a time t will consist of different satellites, obviously. And so if we take a satellite at a time t, it will receive from the neighbors or for the satellites able to communicate with it time data, which are basically the onboard clocks of the other satellites telling it it's 4 p.m. or it's 5 p.m. and so on. And it will record this in a table as well as the time that it received it at, because obviously this is asynchronous data. We don't know otherwise what happens, how long it takes to travel there, etc. So we have time data and a time of reception in our little table. From this, we're able to calculate the error. So that is the error that our satellite had at the time that this data was received. It tells us, well, when I received information from satellite A, I was actually 1 second off from their own time, but a bit later, when I received information from satellite B, I was less than 2 seconds off. So that's what our errors are consisting of. We then do our consensus process from this, the same one that I described, which is inspired from social dynamics, meaning we will remove all of the outliers from our data set to make sure that they don't pollute or interfere with our consensus. From there on, we calculate the time and the rate that we can consider the consensus is ticking at. So all of the satellites have exchanged information, and we say, this is the consensus that they're at, and also this is how this consensus is evolving. And from this, our satellite can then calculate its error in time, meaning the satellites think it's 4 p.m., but all of its neighbors think it's 5 p.m. So there's obviously a 1 hour difference. And it can calculate its error in rate, meaning that the satellite might think a second is a second, but all of the other satellites are running much faster. Clearly, there's a problem. And so we can calculate these errors from the consensus we have just established, and from that, update our own ticking rate. So the satellite will slowly, over time, update its time. And this process that we have here takes place over a period of time for a consensus cycle, and will then be repeated again and again until our errors in time and in rate reduce slow and become smaller, smaller, and smaller, which currently, based on the simulations that we have here and that have been developing, we can get up to around an error of 10 to the minus 7, so not quite nanoseconds, but we're getting there. We have less than a microsecond of difference between all of our satellites in a way that is completely decentralized and resilient, since tests have shown us that we can resist to about 10% of our network failing or becoming malicious. And so this is going to be everything from me, and I'm going to hand over to Beth here.
So now that we've got an algorithm that can give us consensus on what we think the time is, so we have an agreed time, how do we use that information to actually decentralize a satellite network and make them behave physically in a way that is decentralized rather than centralized? So we've already touched on the satellite network. We can picture tens, hundreds, thousands of satellites orbiting above us. But there's a few other things that we need to make decentralization a reality in space. And the first is learning from IoT networks. So there's already been a lot of research coming out, particularly in the last 10 years, around moving IoT networks away from this centralized architecture, relying on a central server or cloud. And there's a few requirements that we've learned from the world of IoT that we can apply to satellites. Things like sharing computational constraints. IoT devices are typically low power. We can't be performing complicated algorithms, so we need to try and keep them as simple as possible. Likewise, on satellites, whilst we can put quite sophisticated computing hardware on there, satellites are reliant on solar power that needs to be prioritized for the core mission of that satellite, not for implementing some sort of infrastructure behind the scenes. So we want it to be as low power as possible. We also have networks of heterogeneous devices. IoT networks are famous for this. The devices come in all sorts of shapes and sizes, and satellites do as well. It's only recently with the introduction of the CubeSat that we're starting to see some sort of standardization in what a satellite physically looks like, but we're still a long way off from all satellites being the same. And both networks rely on sensor data. So for IoT networks, things like smartwatches, obviously you're detecting body sensor data. Satellites can detect a variety of data, things like radio frequency data, optical information, and velocity measurements. And we can use that information to create a decentralized network. But even with all of that learning from the world of IoT, there's still quite a few questions that remain. How do we make this work in the asynchronous, sparse networks that Agathe has been describing? And how do we cope with such a high throughput of data? If you imagine a mega constellation of thousands of satellites, each reporting their sensor images every few seconds, how are we going to handle that throughput of hundreds of thousands of bits of information per second or per minute? And the answer is where my research comes in, is hopefully through distributed ledger technologies, which might be a new term to some of you, but I imagine the term cryptocurrency is probably one that's quite familiar to you, things like Bitcoin, Algorand, Hedera Hashgraph. And this is where this technology comes from. Distributed ledger technologies, famously otherwise known as a blockchain, as the most simple implementation of them, are a way of decentralizing data and information across lots of nodes in a network. So traditionally in cryptocurrency, those nodes have been computers based down here on Earth. In my network, a node is instead a satellite in low Earth orbit. And rather than sharing financial information, as in the world of cryptocurrency, I want to be sharing information on the positions and trajectories of satellites in orbit, with the aim of creating a decentralized map system where satellites can be aware of the current and future positions of satellites for things like automated collision avoidance and decentralized satellite services. A blockchain might be the most simplest implementation of this, but doesn't actually reflect that complex topology that Agathe was describing. So there are other types of distributed ledgers known as directed acyclic graphs, or DAGs, which kind of reflect that topology a bit better. They're much more dynamic, they grow quickly, and we're seeing these implementations in IoT networks today, where they can cope better with the high throughput demands. So my research is looking at how do I combine the synchronized time signal with this computer science from the world of cryptocurrency to develop something a bit more than a decentralized database, but a decentralized tasking mechanism to underpin satellite operations. And the current step I'm looking at is how do we reach consensus, which is something Agathe has mentioned, reaching consensus on time, but I'm trying to reach consensus on a physical location. So tying in this digital world, these algorithms to physical parameters, where actually is a satellite in space. And the way I'm hoping to do this is by developing a new way of reaching consensus on location. So I'll illustrate this with a bit of a simple example. So if we imagine one satellite in a network may witness another one, and this can be done through radio frequency ranging or through optical ranging, maybe a combination, depending on the hardware that already exists on the satellite. And it will report what it's seen to the wider network. The wider network will then check the validity and the correctness of that information. So is that information actually physically possible, or has it tried to say it can see something that's on Mars? And if it is possible, then it's, do we trust that information? Has that satellite provided trustworthy, correct information in the past? Are its sensors broken, etc.? And if they can reach agreement on, yes, we do trust them, then that information will get submitted into the distributed ledger. And the distributed ledger shares that information across every satellite in the network and synchronizes it, so everyone has a copy. And what is important about that is it makes the information immutable. It can't be tampered with. So if one satellite tries to change the history of, oh, actually in the past I was somewhere else, that won't agree with the other satellite's copy of the information. And that provides extra resilience and cybersecurity in this implementation. And once we have consensus on where satellites are and where they're going to be, the next step is autonomy for these satellites. So currently, satellite operations are a very manual process reliant on human beings with email down at the ground station to coordinate the movements and actions of satellites. With distributed ledger technologies, there's a stepping stone built in known as a smart contract, which is similar to a legal contract here on Earth. It's just written in code and executes automatically. So you'll have two or more parties agreeing on a set of conditions. So let's say two satellites coming within a certain distance of each other. And when that condition is met, that is broadcast out to every other node in the network. So they all witness that that smart contract has been executed. They all agree that it's been done fairly, so that it removes ambiguity and increases the speed at which we're able to respond to events. So this can enable things like automated collision avoidance, which, as low Earth orbit is getting more populated, becomes a really big problem. And just to illustrate how populated low Earth orbit is, this is a video from the European Space Agency that's currently showing every object larger than 10 centimeters that's orbiting around the Earth. And this population is growing exponentially. So being able to decentralize satellite networks and make them more robust and resilient, not just to space debris, but to cyber attacks, is a really important problem that we're hoping to solve by learning from the world of IoT networks. And we'll leave it there for today, but Agathe and my contact details are on the screen. Feel free to reach out to us via email or LinkedIn after this if we don't have quite enough time for all your questions. Thank you.
Thank you very much indeed, Beth and Agatha. Last month's webinar was on the current OT cybersecurity state of the global built environment, and the full version of that is available for IoTSF members to watch via our members platform. If you're not an IoTSF member, you can watch a shortened version of that broadcast on our YouTube channel, and I'll put the link, well, I have just put the link in Zoom right now for that. By the way, if you're watching the recording of today's broadcast, please like this video and subscribe to our channel. It helps us more than you know. There's an absolute treasure trove of quality stuff on our YouTube channel, so it's well worth setting the notification alert for any new content as well. Now, I'm conscious that we're approaching the hour or the half hour in India. In fact, it's coming up for 9 o'clock in the evening in India. Let's get to the first question, Beth and Agatha. This one is from Gareth. Why not use Earth-based trusted time sources to regularly resync the local time?
Well, one of the problems that we see with sort of trusted time sources is the fact that you need to transmit that time source in orbit. And it is, if not easy, not very complicated to do tampering of that data or to do jamming and prevent the satellites from receiving this information, or in turn, sort of to have desynchronization based on where this time source is and where things come from. Where the next step as well, with the idea of synchronizing in a decentralized fashion, is that the network benefits from having more nodes and more sort of people and satellites as part of it. So there's an element of, you do not need to trust each other, it's a trustless environment, but you do benefit from collaborating with each other, which can then be a foundation towards better collaboration, for example, for Earth observation data and so on. So it's more of a stepping stone, if you will.
Thank you very much. I think this is more than a comment than a question. This is from our previous presenter, Adam Shostak, the godfather of threat modeling. He says, I think this brilliantly ties the generalized threat modeling approach of realizing that we have a denial of service threat to the system with a mathematical model to help us address that. What's your reaction to that?
We were making similar comments throughout Adam's presentation that there was quite a lot of overlap, not just in terms of threat modeling, but kind of general systems thinking, where you're not only trying to model what can go well and what fits together, but also where those vulnerabilities can be. And as well as having mathematical models and simulations, I think there's a lot of similarities in what Adam was saying around brainstorming and relying on domain expertise to try and identify some of these threats, because cyber attacks on satellites are a new field. So we rely heavily on people like Adam and security experts to give us the information that we need.
Yeah, exactly. And it's also interesting to note that the idea of cybersecurity in space is fairly novel, with electronic warfare actually having been considered a primary threat to satellites. for not very long, I think for the last 5 years, but we're already seeing the effects where it used to be that satellites were considered this completely different model thing that was happening until suddenly, oh dear, we can't get our GPS data. And we've seen it with the war in Ukraine, where suddenly a lot of GPS data with Iridium and Viasat suddenly dropped off, which the government was relying on. And it's because up until that point, nobody had really considered that it's not that you've put a satellite in space, you've basically put a computer, with all the problems that this implies.
All right, no more questions for Beth and Agatha, please. Raymond asks, and I think this, I'm not familiar with this, apologies. AIAA has a task force on space sustainability, where this is one of the biggest problems being addressed. So that's just an observation from Raymond. Any thoughts on that one?
Yeah, I think with this application, it's not just about security. We mentioned that low Earth orbit is becoming increasingly crowded and space debris is a really large problem. And without automated tasking, the risk of further debris being created from collisions is really high. And that does put the sustainability of the orbital environment at risk, and it puts the future of space launches and space-based services at risk. So yeah, this is a really big problem that we need to try and solve.
Okay. Jay, staying up very late in Melbourne, is saying, so you're one, using loss of trusted time sources over an extended period as a scenario for testing decentralized information sharing, with two, the overall objective of building and maintaining a satellite position map, and three, hoping to use this data to avoid collisions. Could the satellites typically afford the computations over and above their typical ops?
Well, that's a fairly good summary of what we're trying to say. So that's some good feedback for us. So we've got the point across.
Jay gets it.
I know, yeah. Thank you, Jay. Even at 1:30 in the morning, he's got it. But yes, so in terms of computational cost, it is something that we really need to try and do our best to minimize. Satellite computation has gotten a lot stronger. You can put things like SD cards on board CubeSats to increase memory. And we've got a lot of radiation hardened hardware that can be a lot more resilient than it used to. But generally, we want to minimize computational costs because the utmost priority has to be the mission critical tasks. So whether that's satellite communications or Earth observation, we don't want any sort of operational hardware or software to be draining power away from those tasks. So the short answer is yes, they can do it, but we need to try and make it as small as possible.
And that's why sort of, at least in the case of my simulations with trying to get time synchronization, the idea is to lengthen the periods over which you do your consensus. And the idea is once you have sort of all of your time data in agreement, you need to periodically do checks, but it doesn't need to be, for example, done every second. And based on the computation that I'm requesting, so for example, median and mean based computations, it doesn't actually take that much of a computational effort in that case. The cheeky answer is also, of course, that our work is still in the early stages. Sort of we're working, I don't know if you're familiar with it, but TRL levels of 1 to 2, so technology readiness levels that are fairly low, where it's a case of proving feasibility more than it is of looking directly at an implementation. So we're working purely on simulations as a timestamp, with the thing being, if this can work, then we can then have test beds that actually give an idea of what a real satellite network would look like, and then implementing it on real satellites. But it's a sort of inching as we go to make sure that all of the steps prove that it's feasible and that we're not just pulling this out of our pocket, pretty much.
One final thought. This is from Raymond. I don't think I'll be able to get time for your reaction, but I'll just say it anyway, out of courtesy to Raymond. There are probably more important degradations of operability than threat of collision and resulting decision to avoid collision threat. Many are environmental, example, solar coronal mass ejections, which are not very predictable. I hope that made sense to you, because I'm not completely sure that I was reading that.
Yeah, it makes some sense. Just add a quick comment on that is that literally yesterday the EU released its new, what was it, the Space Act?
Yes.
That's trying to combat priorities that the EU has in space. And generally, those priorities are about safety and resilience, not very predictable. That's more in the realm of solar physicists than it is for us as engineers. And engineers will try and design radiation safe hardware, but ultimately satellite operations.
All right, I don't know if it was the same for the audience,
going.
but I think you might have
Yeah.
broken up a little bit there. I'm hoping that you didn't and everybody got that. But that's all we've got time for, I'm afraid. I told a lot of people that we had a space IoT broadcast coming up, and there's so many people interested in that concept being presented, and you've certainly not disappointed us. So thank you so much for that fantastic presentation and a brilliant Q&A as well. Next month's IoT Security Foundation webinar, I'll mention it one more time, takes place on the day before the European Union's Radio Equipment Directive becomes mandatory. So on Thursday, the 31st of July, we're calling it Red Eve, and we'll have a special Red webinar. It will feature Richard Marshall of Zytex presenting, and then in a break from our traditional webinar format, we'll have a roundtable Red discussion with the IoTSF Regulatory Watch Working Group. We'll also have the BSI involved. You can register now. The link is on Zoom chat right now, so click on it before everything disappears, before we end this broadcast. Open it up in a new tab. And it's going to be a 60-minute Red special, as I've mentioned, Thursday, the 31st of July, 2025. But in the meantime, that is it for today. My special thanks to Adam Shostak in Seattle, Washington, and Beth and Agathe, who joined us from Glasgow today. Please register for the Red webinar nice and early so that you don't forget. So we'll see you next time for that Red special. Have a good rest of your week. Bye for now.